complex. And now we're doing what? Probability, combinatorics, and then the next unit is statistics. So it does feel like we're switching gears. And it does. That's because we are switching gears. That's why. Okay, that's why it feels that way. I'll just remind you that the reason that this feels like kind of a little bit of a disconnect, and we have a smattering of subjects in this course. We're going to do all this crazy stuff. So this is probability, and then statistics, and then our last unit is on series, sequences and series. So total, right, we have like a whole bunch of stuff we do in this course. And the reason is because we're like answering to our masters, IB in particular, and AB, right? So we want to make sure that, you know, on the IB test someday when you take that, either the SL or the HL test, there's going to be a smattering of things, including probability, statistics, calculus. It's like everything, right? Very different than, very broad in its scope, IB tests are, rather than deep like the calculus HE test is. So that's the reason this is stuck in our curriculum, and it does feel like a little bit of a shift in the focus of what we're doing. So you got the homework sheet in front of you with some dates of upcoming assessments. Tentative, you never know, it might get some more, you know, April snow. You never know. Okay, so just put them on your calendar at least for now, please. I just have just a quick little story to tell you. I was down on my, I took Tuesday off, as you know, here. And one thing I like to do, I don't know, maybe you don't know this about Mr. Chase, but I'm quite the hipster. What I love to do is go down, find some like super expensive indie coffee shops, and then like hit some like hole-in-the-wall music places. I don't know about you, but vinyl, far greater than anything that the digital world has to offer, right? I'm all about my analog, okay? So you go into these old places, you find stuff you'll never find on streaming, whatever. What do the kids use these days? Pandora or Spotify or whatever. No. This stuff is the real stuff, right? You go in there, you pull out one of these old school discs, one of these pieces, little 45, 35. You can go like this, you go. Oh man, that's the good stuff. It's old. Anyway, I was in there, you know, and you go back by hand too. None of this searching online. You come across these gems you'd never find with Google. Like this one. I found this just this past week, and I've never had a screen for this unit before until Tuesday, and I took a picture of this, put it on a nice clean white piece of paper, and really excellent lighting.
You have to bring it in, and we can listen to it.
Yeah, can we?
Oh no, it was way above my price. My price.
So you
limit.
bring the white sheet of paper.
Yeah.
Oh, got it.
Mr. Chase, have you tried playing it?
Too many questions? Thank you. Let's move on. Okay. Sounds good though. I think. Yeah. Okay.
Oh, I bet the wavelength is this, like it's a next sign.
So we'll start today with, see my objective on the board is count stuff. Okay, count. Let's count some stuff.
1, 2, 3, 4, 5.
All right. Well, the warm-up problem today, which appears at the top thing on your sheet too. We have a little note sheet today as we go through these. All right. So it should have taken you no more than 10 seconds to solve this problem. Am I right? What's the answer, everybody? 24. Yes. Good job, elementary school students of America. Okay. That's right. It's 24. Good job. But I want to make sure you have full sight of this. It's called the multiplication principle. Because really, it's even as things get really hairy with combinatorics, as we get to really difficult counting problems, this is still the guiding light for us, right? The multiplication principle. And I want to make sure you've seen this before, I think probably, but this can be visualized as a tree. And every outfit possible, if you were to actually start writing them out, could be visualized in this tree. You might put your shirts here, or your pants here, or your socks here, right? And every possible outfit, like say you want a green shirt and white pants and purple socks. I think that's probably what you want. That's right here, right? That's right here. Every leaf, in fact, down at the bottom, every leaf, if I'm allowed to call it that, since we're using the tree analogy, every leaf corresponds to a unique path through this tree, representing a unique outfit, right? So we have all of the outfits, and we don't have any outfits twice. They're all here, right? And it's easy to count the leaves at the end because we can just multiply to get these, right? So there's a one-to-one correspondence with this diagram and the number of outfits. So not that we'll stop and make a tree for everything, but it is a helpful way to organize your information. If you didn't know how to solve this problem coming in today, which I doubt if you had a problem with that, but say you didn't have any knowledge of how to solve this problem, I think the first thing you would think to do is to start writing it out. And if you were to write it out, you wouldn't just do so haphazardly. You'd be like, okay, let's get our stuff together here. Okay, let's think about first every outfit that contains a red shirt. That might be how you would do it, right? And I think even if you didn't have this, this would be the systematic way you'd start to think through it. Even if I didn't guide you with this picture, you would start to think, okay, well, how would I actually do this? Pick a red shirt and then think about all the outfits I could make with that. And then pick a blue shirt. How many outfits could I make with that? So visualizing this, whether with a tree, and later we'll show you some other ways to visualize some of the things in this unit, is, I think, a powerful technique. So we'll jump into one that has, for its answer, something quite a bit bigger. But I want to make sure you understand, this is still like a tree, right? I don't think we want to draw it, but we can still think of it as a very large tree. So someone just rattle off what the calculation will be, not the answer, but the calculation. How will we get this here? So 26, I hear you say for the first thing, because there are 26 letters. And in reality, there might be some restrictions on those letters, more than that, right? You maybe wouldn't allow for I's or O's, maybe. I think what else you might. Well, we'll say 26 letters. By the way, this is very close to what my Erie insurance policy number is. It starts with a Q and it has some numbers, but the numbers were changed. Okay, in case you're trying to make a claim against me, okay. But that is very similar. My policy number is Q followed by some numbers. So 26 options for the first slot, or if you want to think about trees, 26 branches right away for letters. Okay, now we go down to the next branch. How many, what did it say here? 9, because there are 9 non-zero numbers, digits that we could write. And then for the rest, we have 10 options for each of those because we're including 0, 2, 3, 4. So does someone have that calculation?
2, 3, 4, 0, 0, 0, 0, 0. Excellent, Katie. Go, Katie.
Did I get enough zeros there?
I think
All right, so 2.34 billion. Okay, got it. So actually still not enough if every single person in the world wants them, though. Right? Not everyone in the world does, though, probably, unless you have a really large market share as this insurance company. That would be amazing if you had like 1 out of 3 or 1 out of 4 people in the world using your insurance. That'd be amazing. Okay. So the point is, could you still write this as a tree? You could still draw this as a tree. It would just be big. Okay. Yeah, there aren't enough for everyone in the world, that's for sure, right?
Please be quiet.
And actually, there are many more restrictions too, given the fact that there are lots of phone number areas that we don't go into, right, that are reserved for certain use. So yeah, but the United States, there are enough for the people in the United States, though. Well, then the rest of the world doesn't use 10-digit phone numbers. We have to use the country code at the front, right? Have you ever called international?
Oh yeah, Israel is 972, just in case y'all were curious.
Yeah, if you're in the U.S., you don't have to use the country code. But if you live in another country, you have to dial. Anytime you dial from one country, you use the country code. That was amazing. Wow, yeah. All right. All right, let's look at this one now. So what's different, friends, about this one? This just looks like to me that it's going to be, okay, we got 9 digits, so it's just 9 times 9 times 9 times 9. Why, wait, why though? What's different about this one? Oh, okay. So I see what you're saying. So why is it 9 times, let's start, I understand the 9 at the beginning. We have 9 options. Why 8 though? Okay, so I think that makes sense that if we're thinking in terms of like slots to fill, we have 9 for the first slot, but then we only have 8 to pick from for the second slot, etc. Or again, you can go back to trees. You can think I have 9 options in the first branch, and then on each node of the tree, I have only 8 options, right? So on every single second level node, I've got 8 branches coming from them. All of them look a little different. They're all excluding a different number that was picked just prior. But that makes sense. All right, so someone figure out what that comes out to for us too. Say it again. 3. What? 8. 880. Okay, so good. Or some some folks will tell you that that can be written how? What'd you say? Someone said that.
9 exclamation.
And on your calculator, that can be gotten if you type in 9 factorial. You can get that by hitting 9 and then go to math, PRB, and then number 4. There you go. So that'll be a little quicker for you. It's actually worth. This is such a common thing to ask, I think, that it's worth saying that in general, n items or n people or n digits can be arranged in n factorial ways. It's worth writing that up here, right? There are n factorial arrangements for n things. So how many ways could I permute these people at this table? How many different seating arrangements could there be for these 4 people in these 4 seats? 24, yeah. 4 factorial, right? 4 options for this one. Okay, but once I've sat one of them here, 3 and then 2 and then 1 option here. How many ways are there for you and 6 friends to sit at 7 seats in the theater? 7 factorial, right?
What if you don't have that many?
Personal problem, yeah. Theoretical. We're all about theories in that class, okay? It's all hypothetical.
Wait a second.
How many ways are there to arrange these digits? How many ways are there to arrange these letters in this word? So what's the calculation here? Since there are, let's see, 1, 2, 3, 4. How many letters? So it's 5 factorial. Maybe you'll get used to these numbers too. You'll just know that that's, what'd you say? Maybe you'll just know that's 120 and we'll move on. Okay. So the point is that comes up enough that it's worth mentioning, worth having a notation for factorial. This just comes up a lot. All right, how about this one here? This has a little bit of a different feel, right? But talk to me about filling slots again here. How do we approach this problem? It's like factorial but cut off. Can you say more, Michael?
Just the first like 20 and 19.
So yeah, you have 20 options for the gold, and then if once you've established who that's going to be, you only have 19 people in the pile left. So I think I hear you. And then 18. So that makes sense based on a prior talk a minute ago about how we were going to think about the previous 2 problems. And that's not hard to get. That equals 6,840. Okay. But of course, this could become cumbersome if because in the modern congratulatory age, we might have 10 awards because we want to make as few people feel bad as possible, right? Isn't that true? Right. So we have 20 people. There are 10 awards. There's like a platinum and a zirconium. There's a weird, I don't know, all sorts of different mixed metal. There's an iron award. Okay. Steel. There's definitely a steel in there. Okay. So, yeah, so how would you do it if there were 10? Well, of course, you just say 20 times 19 times 18 times 17 times 16 times 15 times 14, 11. All right. But you can imagine that in certain circumstances that can become a little bit cumbersome. And I would like to come up with a little bit of a faster way to write this. Just like on the last one, we had 20 factorial. That would have been, that's nice. In fact, this feels like 20 factorial. Like Michael said, this feels like 20 factorial, but kind of like cut off. So how could we adjust 20 factorial?
What would be it? Oh,
Yeah?
we can like divide it by the factorial of like
What here?
the 17 here.
Yeah, 20 factorial divided by 17 factorial. And if you're not sure that he's right about that, let's just take a look, right? That's this. Right? And all these cancel out. So we get the calculation desired. Now on this problem, is any of that worth talking about? On this problem, the answer is probably like no. I think we just write that. Let's all just do 20 times. But you could imagine if there were 10 awards, it would save you time to type in on your calculator 20 factorial divided by 17 factorial. That would maybe save you time if there were 10 awards, 20 factorial divided by 10 factorial. So can you give me a formula in general for this situation? If you have n people, say, and r awards, how are we going to run this? What have we heard? Chris, you want to take it?
N factorial over minus r factorial.
He's got it. And that has a special name. It's called a permutation. You've probably seen it before or heard about it, I think. So far, by the way, I don't think anything we've said is like super new necessarily. pretty thought about permutations before. So it has this notation, little n, big P, little r. So on the previous example, we might write 20p3, and that equals 6,840. And the reason that we might mention this even at all is that your calculator has the ability to do this. Feel free to try your calculator doing this. See if you get 6,840. You'll type in first 20, and then go to the math PRB number 2. Maybe. Yeah. Find it. Don't just trust me on this. It might be number 3. I think it's number 2 though. Math PRB number 2. Is that what it is? Okay. But before you go there, you need to type in 20. So type in 20, and then go there and get this, and then type in 3, and see if when you press enter, you don't get 6,840. Now on this one, that amount of button pressing was not worth it. 20 times 19 times 18, please. At all times, just know what you're doing and make sure you understand what's going on under the hood, right? It makes no sense to reach for this without understanding. It's just 20 times 19 times 18, people. It's just a shortcut in cases where it would be harder. This is not one of those cases. All right, moving smartly along. Let's now do the arrangements of these letters in puppy. So how many is that? 1, 2, 3, 4, 5. All right, so what is that then? What is it?
There are 3 P's.
Oh, so see, some of you already caught this. 5 factorial would be a good first guess, but I think all of you are already starting to hear a murmur, or recognizing that that would be an overcounting. So it's, first of all, I think the first thing we want to recognize is the fact 5 factorial is not just wrong, but that it's wrong in a certain direction. It's more than we wanted, right? It's an overcounting. But it's not, let's just not throw it out here, because maybe we can exactly specify the nature of the overcounting, in which case we can fix it. Yes?
So there's 3 different letters, right? 3 different possible letters, P, U, and Y. So,
True.
I think that we have to divide it 5 minus 3 factorial. 5 minus 3 factorial. So 5 factorial.
So divide by 2 factorial or something?
Yeah.
Okay, interesting idea. I think we want to account for this kind of the 3 P's somehow. Yeah. So here's my suggestion. I want to make sure you understand this is very similar to pushy. That was 5 factorial, and that was the correct answer. But here we have 120 arrangements of this, that is 5 factorial, if we subscript P1, P2, P3, right? If we want to count those as being different things, then we would have 120 arrangements. Of course we don't, but let's say we did. And I wrote them all out here. Except no, I didn't. But pretend I did. 120, all 120 of them. Now I've written them out in a very, very special way, though. I've written them out in such a way that here in this column, these are all different if we have them subscripted. But if we remove the subscripts, they're all the same. And so I want to make sure you understand the way we want to view this is 120 counts this whole list, counts each one of these in the list of 120. These are counted separately. But in our list that we want to think about, we want to count all of these as being just 1. Every time we see these, we want to just count 1, and these 2. Well, how many is that? Yeah. So there are 6 in that list, right? So every time we see, for every 6, in our list of 120 things on this list, for every 6 of them, we want to just count 1, 2, for every 6. So now I think we can specify very clearly that we have overcounted by what? We've overcounted by, well, yeah, we want to maybe say we've overcounted by a factor of 6, right? So we can correct 120 by doing what? Dividing by 6, and we get 20, I don't know, maybe you would just say distinguishable permutations. We could just take this top row. Now, the question still remains, it was very convenient that I gave you this list structured in sets of 6, but how would you know that each of these columns should even have 6 in them? Why 6 is still a question that's at large. Where did I get 6 from? Yeah, go ahead. Yeah, he said 2 factorial, but he was wrong. Is that what you're saying?
Yeah.
Okay.
No one can do
So yes, good. Yeah. So how many are going to be in this list? Well, it's exactly the number of ways you could permute P1, P2, P3. We've already talked about earlier that the number of arrangements for P1, P2, P3 is, for three things, 3 factorial. So why did we divide by 6? Oh, that's right, because 6 is 3 factorial. So in general, because this could get messier, on the next problem you can even see. You see the next problem? Right, in general, this could get messy. We just keep dividing by the symmetry, right? We divide out by that overcounting, right? So we can keep doing this. We only saw that happen once with the word puppy, but if there are additional repeats, let's do bumblebee now, then we'll divide by those other repetitions in the list. So the hard task here is, of course, that we be able to count the number of letters in bumblebee. That's the first task. Let's see. Get 9?
Yeah.
Good. Okay. So 9 factorial is a very good first guess, but then just like the last problem, we might want to divide by some things here. What would be one thing you'd like to divide by? 3 factorial for the what? For the b's. And what else do we need to divide by? Another 3 factorial for the e's. What about the u's? You don't want to divide by 1 factorial? Oh, okay. What about m? What about L? I just want to prove that the formula up here does work for every single thing of its kind, right? We just count how many of that thing is there are repeated and put factorial. But you're also right, those who said, let's not do that. You're welcome to not do that. 1 factorial, 1 factorial, 1 factorial is not needed there. But actually, it is a decent check to make sure you counted all the letters correctly, because 3 plus 3 plus 1 plus 1 plus 1 better add up to 9, and it does. So that's maybe worth doing. Whatever. The point is, what's 9 factorial divided by 6 times 6? What's 9 factorial divided by 36? Someone figure that out for us and tell us. Was it 10,000? Did you say? Someone check her on this. Okay. So we can already start to handle some interesting situations here. We're already wading in pretty well into this, right? We're already doing well. Okay, we're on to the back here now. Word. How would you actually do this if someone handed you 4 cards with the letters W, O, R, and D on them? You would maybe take the O, put it on the table, and be like, okay, now I have, really, the O has been decided for me, that's there. Now with the W, R, and D, I will do all the different permutations of those 3 to fill those 3 slots. Wouldn't that be physically what you'd do if I gave you these cards? And how many arrangements does that give? Yeah, anytime we're arranging 3 things in 3 slots, we have 3 factorial as our answer. But, of course, then the next thing I would do once I was done with that exercise is I would take the O and I would move it to the back and repeat the same exercise, right? And that also, of course, gives how many more arrangements? And so, how many arrangements do we have in total as the answer to this question? Yes, 6 plus 6 is 12. Very good, class. Okay. Yeah. Good. Anyone have another way in on that problem you'd like to share? Huh? Yeah, you could also say 2 times 3 factorial, which is clear after seeing this. You can be like, okay, well, of course we can do 2 times 3 factorial. But also just think, maybe you could have thought from the very beginning about that rather than looking at it after the fact. You could think, okay, if I were thinking about a tree here, the first 2 branches might be, where do I put the O? Right? The first branch might be, where do I put the O? Front or back? And then underneath of each of those, you'd have 6 branches, where the places of W, R, and D are. Total 12, right? 2 times 6. All right, we got person A, B, C, and D in a line so that Daniel isn't last. So, I don't know. What is that? How do we get in on that? So yeah, I mean, this is similar to the previous one. We got 4 people, so I guess we could, it's kind of like the O being here, or here, or here, and then arranging them. So I hear some people say 3 times 3 factorial. Think of another way to do it too. What's another way?
So I like how I did it was like first I said like just ignore it. So in a way that Daniel is not last, so it's just everything minus where Daniel is last. So I did 4 factorial and then I did
So 4 factorial represents what?
every like no restriction.
No restrictions, yeah. It represents the number of ways of arranging the 4 of them without restriction. And there's only one situation, or excuse me, not one situation, but one set of situations where we don't want to see, and
Yeah.
those are.
Daniel is last, so it's 3 factorial.
So these, I guess, come out to be the same thing. Both of them are. Hopefully, you've heard how both of them were conceived. In both cases, we get what? Not all at once. You're overwhelming. Okay, yeah, 18. In either case, you'll get 18. Here we have 3 times 6. Here we have 24 minus 6. I like this because in certain situations, these are both about equally easy here. But certainly in certain circumstances, one kind of calculation might be easier than another. It's worth mentioning and figuring out which is easier. 7 card players around a table. Circular table. So we got A, B, C, D, E, F, G. I get it right? Okay. So what's the snag here? Of course, I mean, my first instinct is to say 7 factorial. I think it is for you too. But why is this a little bit of an interesting problem? Yeah, this seating arrangement we have right now, that is the seating arrangement A, B, C, D, E, F, G, is equal to, in our particular situation, isn't this the same game of cards? B, C, D, E, F, G, A, right? Isn't that the same if we rotate? It's like, imagine the card game. Everyone like, okay, everyone get up, let's play a new card game. And everyone like sits down in exactly the same arrangement, we're rotated. Everyone would be like, whoa, hold up, I'm still receiving from and discarding to the same people. This is not a different game of cards. This is, and then everyone flips the table. It's like a disaster. Okay.
Everyone wants the table for their way, it just lifts up the table.
And then it just smashes to the roof. Yeah, yeah. People, cards are everywhere, chips are on the floor. Yeah.
For some people, card games still won't be the same. Variations, right?
Well, there might be other elements to the card game, but. All right, so this is wrong. So how many do we want to keep considered equal in this list? Yeah, every single arrangement has how many others that are we want to consider the same? Yeah, there are like 7 clicks, right? So how can we adjust this? Yeah, which is 720, by the way, if you care. All right, so more on this later. Obviously, we can get to all the examples, but you guys are going to be excellently prepared, I think, for homework number 1 from the book. See you tomorrow.